out and which I left in that packet. These are questions from a very old IB exam. I mean, it says right on top, May 2002. Right? You guys were small. Yeah, small. So like probably 3 syllabuses ago. But I think everything I left in here, is still in the current curriculum, or is once again in the current curriculum. All right, so we left off with topic 3. We had 2 other topics we wanted to bring our attention back to today. The first one is topic 4. Topic 4 was a big topic or a small topic? No, it's a pretty medium topic. I think it was like our 3rd biggest topic after topic 2 and topic 8. So it was, but significantly smaller than those 2. And we did have 5 different subtopics here, right? Kinematics of simple harmonic motion, so our velocity, acceleration, all that stuff. Energy changes during simple harmonic motion, forced oscillations and resonance, and then wave characteristics and wave properties. And much of the beginning of next year, you guys will spend on the higher level version of the wave topic. All right, so in our kinematics of simple harmonic motion, please remember that the most important equation of this topic is not in the data booklet, our defining equation of simple harmonic motion. Please do not cheat and bring that with you to the exam, but make sure that you know it entering the exam. So we have simple harmonic motion is motion where the acceleration, right, is proportional to the displacement, but directed opposite the displacement, or directed towards equilibrium position. Okay, so that is the definition of simple harmonic motion, and you also do need to know that we have angular frequency squared in there. When we are using our simple harmonic motion equations, right, which look like, it looks like x equals x naught times sine omega t. I think that one actually might have a negative sign in it. But when we're using these equations, which do have trig in them, we need to be having our calculators in radian mode. Right? Not degree mode. And we did have 2 sets of equations in our data booklet. We had 1 set, and when I'm talking about the displacement and the velocity equations, right? We had 1 set that's used for if our oscillator is at the equilibrium position at a time of 0, and then the other column is for when our oscillator is at the positive amplitude at a time of 0. Right? So have confidence in the one that you're using. Our next subtopic was on our energies of our simple harmonic oscillators. There are expressions. No, I think. Which is it? There's some in some are in your data booklet, some are not. Which is that? I think the maximum kinetic energy is in there. Maybe kinetic energy is in there also.
Yeah, those are
Yes, so we have kinetic energy, we have maximum kinetic energy, and we have total energy. We do not have the potential energy equation. I suppose you could be a little bit clever and recognize that the total energy should be the sum of the kinetic and potential, just like we said last class for satellites. And that means that potential energy would be total minus kinetic. Right? We do have an expression for total, which says 1/2 mass times angular frequency squared times amplitude squared, and we have one for kinetic. 1/2 mass times angular frequency squared times amplitude squared minus displacement squared. So perhaps, if you're clever, you can combine those together to come up with 1/2 mass angular frequency squared times displacement squared for potential energy. Or maybe you can just remember, hey, if the displacement is 0, there is no potential energy, and if the displacement is at a maximum, then all of the energy is potential. But you should be at least aware that you might need to know potential energy. And then you do want to be comfortable, and this goes back to the previous subtopic also, where in our oscillation do these things, are these things at a maximum and are these things at a minimum? So if we have a pendulum, right, we want to know that as the pendulum passes through the equilibrium position, the speed is at a maximum, the acceleration is at a minimum, right? If speed is at a maximum, kinetic energy is also at a maximum, and potential energy is 0 as we're passing through it. So we want to be pretty confident in that. And then the last subtopic on oscillations involved our forced frequencies and resonance and damping, right? So damping was when we have retarding forces that are taking energy out of our oscillator. We have something called critical damping, if there's so much damping that we don't even have a single oscillation. We want to remember that everything has natural frequencies of vibration. We revisited that at the end of topic 8 with the greenhouse effect. And forced oscillations are when we have damping and we have something that is restoring that energy that's lost from the damping, right? So we're continuing to force our oscillator. And then resonance occurs when the frequency of the driving force is the same as the natural frequency. Then we moved on to waves, and we only spent maybe 2.5 days on waves because we have very little that wasn't reviewed from last year. We definitely want to know how to explain the difference between transverse and longitudinal waves, and we do that by discussing the direction of oscillation of the particles as compared to the direction of the propagation of the energy. We want to remember that not only did we treat waves as rays this year, we also did wave fronts, and we did like Snell's law diagrams with wave fronts, we did reflection diagrams with wave fronts. We want to remember that wave speed does have a special equation that we can derive from our regular speed of frequency times wavelength, and that the speed of all of our types of electromagnetic radiation is the same in a vacuum, and that's 3.00 times 10 to the 8th. Finally, we had our wave properties. So we did do Snell's law this year, but remember it shows up differently in the data book. We did discuss diffraction qualitatively, and we did even get a little bit into our double slit diffraction and having a phase difference and a path difference and getting constructive interference and bright spots and destructive interference and dim spots. We'll do that quantitatively next year. And we revisited superposition, which was when we had multiple wave energies at the same spot on a medium at the same time. And sometimes the energies can add to each other, and we call that constructive interference, and sometimes the energies can subtract from each other, and we call that destructive interference. Other topic 4 issues. All right, then we had topic 5, which was our electric currents and circuits. So we started off, right, with a section called electric potential difference, current, and resistance, and then we have a second topic called electric circuits. And this was actually a fairly small topic. We did meet our friend the electron volt, which we didn't spend much time with back then, but we spent much more time with in topic 7, and mega electron volts and giga electron volts sometimes. And most of you know the definition of that. It's the kinetic energy gained by a single unbound electron as it crosses through a potential difference of 1 volt. I think we just saw a few questions just this week where we had to utilize our knowledge of the definition of the electron volt. We need to remember that electric current is based on our electromagnetism and our force per unit length of parallel current carrying conductors. We want to know that resistance is merely the ratio of the potential difference across something to the current going through it. We had a new way of thinking about resistance, which incorporated our resistivity. Is that right? Yeah? All right. So that incorporates our resistivity. So resistivity is kind of a function, it's a material property. It can change with temperature. Length, it refers to the length of our conductor. So typically we're dealing with this equation when we have like a wire, right? So the longer wire has more resistance. And then this A is the cross-sectional area of the conductor. So a thicker wire has less resistance. A thinner wire has quite a bit more resistance. And then we finished up by comparing ohmic and non-ohmic behavior. Most things are ohmic, at least within narrow temperature range. But things like light bulbs are particularly non-ohmic. And we can identify that by looking at a potential difference versus current graph. an ohmic thing should have a very linear relationship. And, I'm not careful, I'll get this wrong. A light bulb, I think looks like that. And then there are actually some things that are non-ohmic but actually have a larger resistance at greater potential difference. Then, I might be wrong about the way that goes. I might be wrong. Don't quote me. All right, and then the second half of chapter 5 was on our circuits. So we did meet EMF, electromotive force, which is not a force at all. It's the power supply per unit current delivered by the cell. And our kind of wrong way, not wrong, but our not technically correct way of thinking about EMF was the potential difference of our power source. The reason that's not entirely right is, are we considering the internal resistance of the power source or not? Because the EMF does not consider that. But if we were to measure the potential difference of our power source, well, that does have the internal resistance built in. We did review our series and parallel circuits, so we want to be comfortable with, if we have resistors in series, that increases the total resistance of the circuit. If we have our resistors in parallel, we will draw quite a bit more current from our batteries, so that lowers the resistance. We also want to remember that we did see scenarios where we had combination circuits. We did not have anything really more complicated than this, where we would have like equal resistors, right? But we did pay some attention to combination circuits. We, again this year, learned about ammeters and voltmeters and how we connect them into circuits, and that an ideal ammeter should have no resistance, and an ideal voltmeter should have an infinitely high resistance. And then we met a few different sensor devices. We had light-dependent resistors whose resistance decreases when light shines on them. We had we just called them thermistors. And we said that thermistors when their temperature goes up, their resistance is less. That's actually not always true. That's called an NTC, negative temperature coefficient thermistor. There are opposite kinds also. The only kind that we looked at was the kind that have less resistance when we heat them up. We also looked at strain gauges, but I've never once seen a question about a strain gauge on an IV exam. Okay, so that's the first 5 topics. We'll do the next 3 on Tuesday. So we have about 20 minutes remaining. What I'd like you to do is go ahead, well, why don't you first in your foursomes, if you've gotten to any of these, compare your answers, right? Once you finish comparing, then I want you to work together. So if you didn't actually get to look at any of these yet, no big deal. Let your partners compare, and then you'll jump in at the point where everybody's starting fresh questions. All right? So we'll do that. If you want to check any answers with me once you've compared, feel free.